Everyone. So we're going to continue our discussion about the whole, it was the Boltzmann distribution and the partition function, and we're going to talk about how it relates to something called thermal radiation and the Planck distribution. Basically, when we have an EM wave that is actually causing the thermal equilibrium, how is that going to play a part? Now, before we continue, I just want to do some quick practice questions similar to things that we've done before. So you can pause the video, work on this yourself, and we'll go over in a second. All right, so we want to figure out what the binding energy caused by gravity is around some sort of sphered surface. In particular, we're basically going to assume that this is some sort of like star, if you will. So the way we find this out is we take the gravitational potential energy for a between some specific point in time, usually around massive objects, and we're going to integrate it. And we're going to try to figure this out and see if we could get to this equation here. So again, we know what the final solution is, so we just kind of have to fool around with this until we get to here. All right, so first off, so there's two parts here. There's the mass of the shell part and the mass of what's inside. The shell is essentially the, if you will, the mass of the very outer crust, which is actually going to be pretty much like picked apart, and then the interior is everything else. The way that they describe the binding energy is it's basically the amount of energy that would be required to pick apart a sphered object by counterbalancing the gravitational energy holding it together. So the shell is going to be the surface area of it. We find that surface area by doing this. So this is the cross-sectional area times the density, and then we have dr because it's going to be over that small distance. But the interior is just everything involved. So that just ends up being v times rho. So from here, we integrate with respect to dr. We can replace the surface area and the volume with their equations so that because we know that they are r dependent, and then the densities can actually be pulled out since they're constants, and we get left with this function right here. So we're just integrating along r to the fourth. So from there, that integration is pretty straightforward. It becomes r to the fifth. Now from here, the goal is to take this and bring it back to this solution. So for example, we want to replace it with big R and big M somewhere in here. So there's no rho involved here. So what I can do is I can actually replace the rho with this equation, m 4/3 pi r cubed, because we know that it's mass over volume. From here, this is actually going to cross out the squares there. We end up having a 16 here and here crossing out, and then 9 and 15. We can actually simplify that, and we can already see that that's going to simplify to the 3/5. We have the g now. We have the m squared. So let's continue on. Yeah, the r to the sixth and r to the fifth are going to cross out, leaving us with just a single r. So again, the whole thing is to do the integration that they want and then try to think about, well, how can I turn this into what I have here? Look for what things are different and see how you're going to replace them. All right, so using that equation, pause the video, work on this yourself, and we'll go over it in a second. All right, so now we're using the values for the sun. They give us a bunch of the numbers, so it's just a standard plug and chug. And we get that the binding energy of the sun is going to be about 2.29 times 10 to the 41 joules. So a decent amount. This question, you could pause the video, work on this stuff, and we'll go over in a second. All right, So they're telling us that the thermal kinetic energy is going to be equal to half the gravitational energy, and then they tell us the number of atoms, and they want to figure out the average temperature. So we know that the temperature is related to the total kinetic energy. So what we're going to do is we're going to use this equation. We know that the kinetic energy is equal to 3 halves n tau, and we know that that's going to be equal to half of the gravitational. So we can move this, solve for tau, replace the tau because they want an actual temperature. We're going to replace that with T by throwing in the Boltzmann constant, like right there. And then we just plug the numbers in and chug out our answer. And we get this 5.5 times 10 to the 6 Kelvin. All right. So, to come up with the Planck distribution when dealing with thermal radiation, what we're going to do is we're going to consider a case where we have a cavity. So we have an open space that's going to be exposed to EM radiation. So the EM radiation is going to come in, and it's going to cause the particles to kind of move around and resonate and all that stuff. And it's going to come in until the whole system is brought to thermal equilibrium. Now, in order, you kind of just kind of hinted at what we're going to be doing, but in order for it to reach a thermal equilibrium, the EM wave has to end up resonating with the cavity. And as we know, resonation from previous physics classes is usually causing a standing wave. So a lot of the stuff that we're going to be doing is going to be based off of this concept. Now, if you recall, when we resonate something like a string, let's say, where it's fixed at two ends, or an open pipe that's open at both ends, we end up knowing that the standing wave can only occur if we have the same parts of the standing wave at both locations, either two nodes at two locations or two antinodes. Um, and in particular, it's always going to end up fitting half a wavelength or an integer number of half a wavelength. So we could fit one wave, we could fit, we could fit half a wave, we could fit one wave, 1.5 waves, any sort of integer half wavelengths, just like this. So we could fit half a wave, 1.5 waves, or in general, n.5 waves. Now, we're going to use this n to usually refer to the mode in order to specify what type of standing wave. All right, so the first mode would be the first standing wave that could be produced, second mode, so on, so on. All right, now we also want to kind of use the definition for angular frequency. So as you know, angular frequency is just 2 pi f. As far as why we're doing this, it's mainly because of the fact that, again, there's always a 2 pi factor involved. So this just kind of simplifies it. So we have the omega here. It's equal to 2 pi f, which we know we can replace with c over lambda, which using our equation from before with what the lambda is, we get this. So again, this is going to tell us the fact that the frequencies that can fit and cause a standing wave or a resonation pattern is going to be some integer number of an integer number of frequencies. So like for example, if the first mode is 50 hertz, then the second mode would be 100 hertz, and then 150, and then 200. So it's going to go up by some integer number of whatever the first frequency is. Now, as we know, the energy for a photon that comes in is going to be equal to HF. Now we can rewrite this in terms of the given terms of H bar and omega that, like I said, that we were going to want to talk and say that the energy for whatever the resonance pattern is going to be equal to this, S H bar omega. So S is going to be some any positive number. It could also include 0. And for the most part, this is very similar to Q in that it's pretty much the number of energy units involved. So this term is going to refer to the frequency, um, or is going to be related to the frequency part, mainly the omega part. And the S is going to be related to how many there are. So here are two examples of that. So here we have two photons that are coming in. They're the same mode, so their omega values are the same. And we can see that both of these are representing half of a wave. But this wave, or this photon pattern, is going to be have a much bigger amplitude than this one. And that's caused by the fact that the coefficient is 2. It's bigger than the one here, which doesn't have a coefficient. And here's just another one. So here we go to a different mode of frequency. So we can see that it changes from being half a wave to a full standing wave. And then once again, we can increase the amplitude by changing that coefficient. So that's pretty much all this is doing. Um, all right. So we're going to be finding the average number using the partition function, very similar to what we've done before. Because remember, we do have a way of figuring out the average number of things. So if you recall, our partition function looks like this. Now we have an equation for the energy at any mode available. So we're going to replace that for like this, SH bar omega. Now, once again, the way we're going to evaluate this is by getting rid of a lot of these terms, replacing the h bar omega over tau with an x, so that we have x to the s. And then we know that this summation, x to the s, is going to be equal to 1 over 1 minus x when x is very small, or less than 1. And for the most part, we could pretty much assume that that's going to be the case. So we end up getting the same partition function that we've gotten in the previous parts. But again, now it's without the s term. We also know how we get the probability. The probability is done by taking that Boltzmann factor and dividing it by the partition function. So the energy at a specific state right here, the Boltzmann factor based off of that divided by the total number of states. And the thermal, we know, is a added sum based off of a weighted sum of all the numbers times the probabilities that they occur. So combining both of these, we get this. So again, it's a lot of the same stuff that we've done in previous parts, and you're going to see that a lot. So there's going to be later parts where I'm going to bring up, once again, like, oh, we're going to find the average number of blank, and it's going to be done the same way. We determine the partition function and the probability, and then use that to find a weighted sum, and yada, yada, yada. So as you could probably guess, what we're going to do is we're going to find a way to relate this to some form of the partition function. So we're going to do another sum actually to kind of find a way to simplify this. So what we can do is we can replace the h bar omega over tau with a y, and from here we can actually see that this term really is just the derivative of this term without the s. We had to throw in a negative in there just to be safe, but you can actually see this yourself. If you take this term, you take a derivative, you'll end up getting this. So we're going to take the sum first, and that's what we do here. It's the same thing from before, but now what we're going to have to do is we're going to have to take the derivative of this with respect to y. So taking the derivative looks something like this when you do the chain rule. So combining this back to our average value, the thermal average value, what we end up having is this relationship. So from our evaluation up here, divided by the partition function. We could also bring this down here, which I think I do Here, yeah. And this is what we call the Planck constant. It basically is giving us the average number of photons that are creating one of the frequency modes. All right. So if we have a cavity base setup, we can figure out how many photons are going to end up having to resonate within there based off of the frequency and based off the temperature that it's going to be reaching equilibrium in. Oh, we can take this one step further and we can use the definition for this average number of photons with the average energy um, by just literally plugging it in and multiplying it by h bar omega to get this. So again, now that we have this, we could actually use this a lot in order to come up with other equations. Now, as you know, we have to define things like the classical regime or the classical limit, things that are going to not really be affected by quantum effects. And that's going to occur when tau is much greater than this h bar omega. Basically, it's relating to that the temperature energy or the kinetic energy is much bigger than the photon energy. So if we take the energy of the photon, we end up getting that if tau is much greater than h bar omega, then that E function is going to actually simplify to this term. This is one of the approximations that we've talked about. Um, so from here, we can already see that all this is going to simplify to tau. Basically, in the classical regime, the average energy in the system is going to be equal to the temperature. So pretty much what we would normally expect to occur, since as we know, this temperature term is typically defined as the average kinetic energy of the system. Um, all right, so uh, this is looking at the because so we know that EM waves are being produced by an electric field and a magnetic field. So we're saying that in this cavity, if we have an EM wave going in, we're going to look at that electric field aspect of it. So there are, so it says here that we have two independent polarizations. So here is the electric field going in one of the directions, the x direction, and it's going to end up being equal to this entire term. So this is the time aspect, and these are the x, y, and z aspects. Now, one thing that we're going to do is go back to the wave equation. The wave equation basically says that we're going to take the second, if you don't know what this term is, I believe it's called the del operator. It's a short way of saying that we're taking the second derivative with respect to the three dimensions of something. And that's what we're doing here. So we're taking the partial derivative with respect to x, y, and z. And we end up getting, when we do all this, it's going to end up equaling to this, the partial derivative with respect to time. This was something that is found from one of the previous levels of physics. I'm not going to go over right now where it comes from, but again, if you go into Physics 126 and you look through your notes, you probably will have seen something like this, though it would have been written differently. The wave equation in those terms were only one-dimensional based, so you probably would have only seen it as the second derivative with respect to x equals this with respect to time. But since we have a three-dimensional object, then we have to actually have it as a function of three dimensions. So when we do this, when we take this and take the partial with respect to the three dimensions, we get this. Now this is simplified because there's all these sine terms that are going to end up canceling out. because when we take the second derivative of this, we get uh, the derivative of what's going on in here times this entire thing, and then the derivative of what's in here times this entire thing. So each one of these derivatives is going to have all of this garbage. The only thing that's going to be different is whatever the derivative of is inside of these sine terms. So essentially, it's really could be thought of as doing the second derivative of this stuff, the second derivative of this, the second derivative of this, uh, and then the second derivative of this. So yeah, this ends up giving us a relationship between the number of modes in the x, y, and z direction and the frequency. All right, so that equation can actually be simplified to look something like this. And we end up getting this equation that's again relating the number of modes to the frequency. And then we could come up with the density of modes within the box. So the way we're going to do this is we're going to use this definition. So this is going to be equal to the number of modes between some frequency and then another frequency. So it's between one mode to another mode. Now, the way we're going to end up doing this, it's a little confusing, so bear with me. We're going to consider an eighth of a spherical shell that has a thickness of dn, and the radius is of n. So these ends are not the same as this end. Just throwing that out there. And we're going to say that the shell is going to contain some number of modes, and then it's going to be having two independent modes of polarization. So our distribution is going to look something like this. All right. So the number of modes between omega and omega plus d omega is found by the two independent modes of polarization, the 1/8, and then this is the spherical shell aspect. So that's where all this is coming from. Um, don't really worry too much about this because this is just going to be an initial derivation. This process will actually come up later on, but again, it's doing the exact same thing, but with maybe some slight terminology changes. So we end up getting this for our density. So taking our value for n, um, and then we could take the partial derivative to see what this term is going to be equal to. So we can already see that it's going to be equal to L over pi c. So combining this in for the n and this in for the dn over d omega, we get this. And then the L cubed can be simplified to being V. So this ends up being the density based off of the frequencies, based off the modes. We take this one step further and relate this to energy density. So as you could probably guess, the energy density would be the average energy times the density times the d omega. So plugging this all in and then integrating. Sorry, not integrating. We don't need to do that part, but what we could do is divide the V over. So this ends up becoming the energy density, the energy over the aspect of volume. We're going to actually redefine this concept with this little u. So if you see the little u, that's supposed to be an energy density term. And that's going to be equal to all this junk right here. So this is what we're actually using to call the Planck radiation law. And it's basically representing the energy density related to the frequency range. So that's pretty much it. we'll do a quick question, practice question with this in a second, and then that'll be the end of this first video. All right. So we can actually rewrite this so that we could find what they call the radiant energy density as a function of temperature. We're going to do this by replacing the h bar omega over tau with an x. So our equation ends up looking something like this. And then from here, we're going to integrate from 0 to infinity. So here we're just going to end up getting the u. Here we have to end up integrating this part. So this one ends up having a basic definition of pi to the fourth over 15. So from here, we end up having the energy density now as a function of temperature rather than as a function of frequency. Now this one is actually called the Stefan-Boltzmann law of radiation. So again, pretty much similar, figuring out the energy density given off by some sort of radiation, but now it's we have two different forms. We have one that's based off of frequency and one that's going to be based off of temperature. We can use this to actually figure out the surface temperature of any sort of hot body, such as a star, and determining the frequency that will end up resulting in the maximum energy emission. So, as you know, we find the max of anything by taking the derivative of it. So we can go back to the equation that we had before with the x's and just take the derivative of this with respect to x. And then from here, because all this stuff doesn't really matter, it's only about this stuff, we end up getting this. 3 minus 3e to the negative x equals x. And that's from setting it equal to 0. When we solve this, we end up getting that the maximum value is going to be equal to when h bar omega over kbt is approximately equal to 2.82. So there is a distribution of which frequency is going to result in the most energy emission. So from here we can actually figure out a relationship between the frequency of the light being emitted and the temperature at the surface. And like I said, it's going to be equal to this function. We can actually relate all this stuff that we've had with entropy. So we could think of this as the entropy of the photons by taking the energy and doing this, including this dt aspect, taking the derivative with respect to temperature, and we end up getting this. Simplifying a little bit further, and so this ends up being a relationship of the entropy based off the temperature based off of the photons. All right. So we're going to talk about something else called energy flux density. So energy flux density is represented by Ju. This is pretty much the power or the rate of energy that's being transferred through a surface. So again, this is relating to a star when it's emitting its light. That energy flux as it goes out is going to be pretty much consistent. So here we have the energy flux density. It's going to be, this is our actual energy flux term, and then this is the surface area that it's passing through. We can replace the energy flux with this, a term of alpha times u, and then Again, we can kind of take it one step at a time. Um, we can include the an L term on both the numerator and the denominator. That way, this replaces with a V. This L over T can actually be replaced with C, like that. Um, and yeah, so here we end up having the energy flux density now being related to this stuff. This alpha term is just some sort of constant. It's a what they call a geometrical factor. Um, it's mostly going to be equal to 1/4. So the energy flux density when we plug that in is going to be approximately equal to this stuff. Um, and because the tau is the only real variable in that equation, it gets written like this, where this is actually being defined as all those constant terms, or uh, more simply put, 5.67 times 10 to the negative 8. This is the Stefan Boltzmann constant. Don't confuse this with entropy, even though they're both given that sigma term. They are vastly different. This is a constant, so it's not at all related to entropy. Um, so this is pretty much saying that any object that can be considered a black body will end up radiating energy based on its temperature. So we can actually do this for things like stars and any other sort of universal object in order to kind of find find values of locations, or what the heat would be like at a certain location in the solar system based off of the temperatures and stuff. All right. So here's a quick question where you get to kind of practice doing that stuff. So you could pause the video, work on this stuff, and we'll go over in a second. All right. So here they say the total energy flux at the Earth based off of the sun is called the solar constant. Um, and we could do this by basically integrating along the emission wavelengths based off of the Earth Sun distance. So the solar constant is going to be equal to this. And they want us to show that the total rate of energy generation from the sun is equal to this. So this is the power, if you will. So first, we have the energy flux density being equal to this solar constant. So this is the energy flux at the location of the Earth. And then this ends up being the distance to the Earth. So the energy flux can be rewritten from our definition as being the energy flux density times the cross-sectional area at that distance. So basically the whole idea is that the Earth is only absorbing a small amount of the energy along that entire sphere by the time it gets to it. So the cross-sectional area is replaced with this, or the surface area is replaced with this. So plugging in all the numbers, we end up getting that the energy flux, or the um, the power, if you will, is equal to this 3.85 times 10 to the 26, or roughly about 4 times 10 to the 26. All right, so we're going to continue on with this in a bit. If you have any questions, please let me know. Otherwise, I'll see you later.